All right, atmospheric pressure and pressure gauges. So when we're talking about the atmosphere, the entire atmosphere is a fluid. And if you guys remember back to our first notes, gases are compressible, meaning that it makes it really hard to check on density or check on our pressure, because pressure is related to density and height. Well, density is also related to height, because the higher up you go, the thinner the air gets. There's less air pushing down on it. It compresses as we go down, meaning it gets really complicated to do any stuff with it. There are equations that I had to do in college with astronomy. You guys don't want to have to do it until you get some calculus under your belt. You're taking an algebra-based class, so we're not going to mess around with that. So even though it's hard to measure, we can use a change in pressure instead of our pressure formula. So pressure at sea level, that's what we're going to call P naught. That is our pressure, not peanut, sea level. And that is around 1.013 times 10 to the fifth pascals. So if you guys remember back to the last section of notes where we looked at how much pressure is pushing down on us from the air, that's right around 10 times as much pressure from the air on you as you on you. Yeah, cool beans. So remember that pascals are the same thing as newtons per meter, so we can write that as newtons per square meter, but there are other ways to write it. 101.3 kilopascals, that's just 1,000 pascals. Another way that we can write it is 760 millimeters of mercury. There are a lot of weird ways to measure pressure, because a lot of them came around before the metric system was standardized. But the easiest one on here that you guys will use is that an atmosphere of pressure is just 1 atmosphere. Wow, that's pretty cool. Makes it nice and easy. I like to use that one. The cool thing about all those is they're on your equation sheet, so feel free to use those. But let's try out a problem with this. Let's say we've got a cup of water. Here's my, that's a weird looking cup of water, whatever. We got a cup of water with a straw in it. There's my straw. And then let's say that I come along and I put my thumb on it. There's my thumb. There's my little nail, my weird looking lines on my thumb. I put my thumb on it and I use it to pick up water. You guys have all done this. You've gone to a restaurant, you start picking up water and your mom starts yelling at you as you go out and you drop it on your straw wrapper where you squinch it up and then it turns into an inchworm as it expands with the water. You know what I'm talking about. So when you pick it up and pull it out of the water, it still holds some in there. There's your thumb, or my thumb again, weird knuckle and all that junk. This is sealed, so no air can flow in and out of it. We'll call this inside of there pressure 1, and we'll call the air out here pressure 2. So I want to know, how does P1 compare to P naught? And I want to know, how does P1 compare to P2? So take a second, think about it, pause it, come back in a second. All right, hopefully you guys recognize that P2 is equal to P naught. It's just atmospheric pressure, so P2 equals P naught. So whatever P1 does with P2, it'll do the same with P naught. Well, think about it this way. Is that water that's in there, this little bit of water, is it moving? If it's not, that's got to mean there's a net force on it that's equal to 0. You may notice it dribbles a little bit out, but overall it's mostly staying in the straw. Well, if I look at the net forces on it, I've got the force of gravity. Everything's got gravity on it. But what's holding it up? Well, obviously there's some type of pressure keeping it in there. If we look, P1 is the pressure from the straw, of the air in the straw up here. That's got to be pushing down on it. That air in there wants to expand. Air always wants to expand. The only reason it's not expanding off into space is because gravity's pulling it down. So we'll just call this the force of P1. but it's not moving. So that means there's got to be an equal and opposite, I went a little too big there, force of P2 holding it in. Meaning that the difference between the force of P1 and force of P2 is equal to the force of gravity. So that difference in pressure is what's holding it in there. So in this case, that means that P2, which is equal to P naught, is greater than P1. So if you ever wanted to know now, you can just tell your parents you're doing science when you're making a mess at the restaurant table. All right, so let's talk about gauge pressure. Any pressure measured above, not about, above atmospheric pressure is called gauge pressure. So what we have here is our absolute pressure. Absolute pressure is going to be equal to P naught, which is our atmospheric pressure, plus, well, I'll write it out and then we'll do it symbolically, is going to be equal to our atmospheric pressure plus our gauge pressure. So if you guys have ever measured the pressure of your car tires or a bike tire, when you put a pressure gauge on it, that gauge is measuring how much more pressure is in your tire than the air on the outside. That little thing that pushes out, it's got the same force on both sides, so you put it down on that tire, then there's more force in there. And the amount it moves out is related to how much extra pressure is in there. So we look at absolute pressure, and that's just represented by a P. Atmospheric pressure is P naught, and gauge pressure is P sub capital G. Let's talk about U-tubes. And I'm not talking about the platform that you're watching this video on. So back in the day, the way they would measure atmospheric pressure is they would have one side of a tube closed and one side of a tube open, and the amount of extra pressure from the air pushed whatever fluid was in the tube higher up, and then they could tell what the atmospheric pressure was based on how high or low the fluid would go. But the cool thing about U-tubes is that we know pressure on one side is equal to pressure on another side because pressure at any given depth is going to be equal. So what we can do is figure out densities of fluids we don't know based on how far they go up a tube. In the case of the one where we have a fluid going up a tube, we can tell air is one fluid, and then let's say mercury, millimeters of mercury, is the other one. So in this case, let's say that we've got a fluid here on the left and a fluid here on the right. Let me check my notes. The one on the right is water. And water, we know, has a density of 1,000 kilograms per cubic meter. And on the left, we have some type of oil. You don't know what type of oil it is. It's just some type of oil. And we're going to try and figure out what its density is. The water goes up to a height of 80 centimeters in our tube. And let's say the oil goes up to a height of 107 centimeters. Let's do this practice one together before you go pausing. Let's just do this one on our own. So we know at this given depth, the pressure is the same in every direction. For a given fluid, no matter how deep you are, whether it's two different fluids, it's always got to have the same pressure at the same depth. So what we can say here is that the pressure on the left is equal to the pressure on the right. We know that pressure is just equal to rho GH. So I'll put rho GH for both of them. This one on the right is our water. This one on the left is our oil. So we're trying to figure out rho. They've got the same G, so we can cross that out. So what we're seeing now is it's just a proportionality. The height is inversely proportional to the density. In this one, we have our rho oil times the height of oil, which in this case is 107 centimeters. Doesn't matter the units on this one. They should cancel out on both sides. That's true of any proportionality. We have 1,000 kilograms per cubic meter. And we have 80 centimeters on this side. So what I'm going to do is plug this into my calculator. Beep, beep, boop, doop, boop. Rearranging this to solve for oil, I get 1,000 times 80 over 107. And I find out the density of this type of oil is 700 48 kilograms per cubic meter. Radical. So now what I'm going to have you guys do is try out some problems on your own. And on this one, we're going to, number 23, get another YouTube. I will unpause the video when I'm done drawing. All right, in this case, we've got oil and water again. This time, we've got a different oil, so it has a different density. That's what we're going to try and find out in this one, row of oil, question mark. In this case, we have a 50 centimeter column of oil, and 15 centimeters below it, we see the water level on that side. So what we're going to try and do in this one is now find out what is the row of oil. I'll give you guys the start that the pressure of the oil is equal to the pressure of the water. I want you to go about trying to solve it. Pause the video here. Try it out on your own. If you get stuck, go ahead and unpause. The answer will be up momentarily. All right, so just like last time, I canceled out gravity because it's the same on both sides. But the tricky part of this one is where do you measure the depth from? And an interesting thing is you can just ignore all of this water down here. As long as you're starting from the same reference point, that's all you need to do, because we're just comparing at a given depth, because it should be the same here, the same there. Given depth, same thing. So that means that if this is 15 centimeters below, our water should be 35 centimeters deep at that point. What we can do then is plug in 35 centimeters times the density of water is equal to the density of oil, etc., etc. And you guys see how I set it up in the last problem. We'll just go ahead and solve for the density of oil. Boop, boop, that's the sound of solving. And we have 700 kilograms per cubic meter. Rad. We're going to do one more problem. I'm going to pause it, set it up on the board, and then you guys can go ahead and solve it. Awesome. So this problem actually teaches you about what is the maximum length that you can make a straw on Earth where it will still work. So on this YouTube, we have a sealed end this time. And inside of this over here, we have a vacuum. Is that UUM or is it VACCUM? Whatever. You know it's a vacuum in there. Nothing in there at all. So the only difference is there's air on this side. You notice there's a difference in height. When you use a straw, you're actually making less pressure on one end, and then the pressure on the outside pushes it up. So what you're looking for in this problem is what is the height difference, or what is the maximum length that a straw can actually suck water up a tube. Go ahead and give it a shot. I'll unpause and we'll go over it together. Okay, so in this one, like normal, the pressure on the left has to be equal to the pressure on the right for a given depth. So I set it up. Things on the left side, we've got air, which is atmospheric pressure, plus the pressure of this water over here. Then on the right, we've got the pressure of the water on this side. But we can make it easier on ourselves. We're not trying to find out any of this. We just want to know what's the difference in height here. So we just take this as our baseline right there. And what it does is gets rid of any water that's on this side. This just became a lot easier. So what I do is I plug in for atmospheric pressure, which is 1.013 times 10 to the 5th pascals. And then rho GH for water. This is just equal to rho GH. Rho of water is 1,000 kilograms per cubic meter. Gravity is 10 meters per second. And our height, the depth of the water here, the difference in height from the sides is what we're going to try and solve for. So I divide by 10, that moves the decimal point over 1, that's a 4 now. Then I divide by 1,000, that moves it over 3 more times, which means that this is now 1. So it looks like the height that we're going to get here, or is that 2? Hold on. It's 2. Here we go. 10.13 meters is the height that you can use to make a straw out of, or the height you can suck water through a straw. So this is about the height of a 3-story building, which is pretty cool, but to get an actual vacuum to do that is kind of difficult. So you probably won't be doing this anytime soon. But if you want, you can do on your own time what is the lowest pressure the human lungs can produce, and you can figure out the maximum length of straw you can find. I wouldn't recommend trying to do it physically. Just do it mathematically so we don't have any medical emergencies on our hand. Let's go back and solve one more problem using what we learned about gauge pressure and absolute pressure. So let's say I've got a lake, and I want to find out what the pressure is 100 meters below the surface. So find which pressure do I want? I want to find, the pressure 100 meters below the lake. So this would be your gauge pressure. Find P sub G 100 meters below surface of a lake. And you guys can work on that. I'm going to give you a part B too that you can work on. And I want to know in this one, find P, so this is your absolute pressure, 100 meters below the surface of a lake. Go ahead and pause the video, work on it. When we come back together, then we'll go over it. All right, here we go. And what we look for here, P is equal to rho G H. That's 1,000 kilograms per cubic meter times 10 meters per second times 100 meters. And what we should get is add a zero, add two more zeros. So that's 10,000, 1 million. So that's 1, 2, 3, 4, 5, 6. Yep. Looks like the numbers add up. Pascals. Or 1 times 10 to the 6th pascals. Or 1 megapascal. Cool beans. Now all we do for that is we add on atmospheric pressure. This is our gauge pressure. Atmospheric pressure, or absolute pressure, is just equal to atmospheric plus gauge. So I have 1 times 10 to the 6th pascals plus approximately, that's this guy right here, plus approximately 1.013. In this case, I'm just going to call it 1 times 10 to the 5th. It's pretty close. And when I add those guys together, I get 1.1 times 10 to the 6th pascals. So 1,100,000 pascals. And that'll do it for our pressure, atmospheric pressure and gauge pressure notes.